Okay, so as he said, my name is Queralt Guerrero, and I'm from Spain. I work in a private company, which is Geociencias y Exploraciones Marítimas, also known as iGeotest. And I'm going to talk about marine geophysical investigation for the offshore wind farms and submarine cables interconnection between different areas. So here in the presentation, I'm going to start with an introduction to put in context the works and the projects that we are going to include in this talk. And then I briefly explain the most common geophysical methods that we use in submarine interconnections and cables projects. Then we will show some examples of the results obtained in one project. And then I'm going to show a summary of the talk. So here we can see a global map where we can see the huge amount of cables that are worldwide. So in the last 35 years, the seas and the oceans worldwide has been converted from to be clean of submarine cables to be built in an extended net of submarine cables. Most of them are related with the telecommunications. So nearly every corner of the globe is now physically connected. If we go to Europe, it's also the same line as the rest of the world. Specifically, the need of the marine electrical interconnections between different regions and the proliferation of the wind farms, mostly in the north of Europe, lead the installation of thousands of kilometers of submarine electrical cables. So Geociencias y Exploraciones Marítimas company developed different projects around Europe in the recent years, all of them related with the marine electrical interconnection. So here you can see some of the most relevant and most important projects that we developed. So this experience in this kind of marine investigations allow defining the most suitable geophysical techniques, the necessary equipment to be used, and the vessel requirements to achieve the demanded technical specifications for these projects that they are often placed in complex working areas. These projects normally involve interconnections between two islands, between continent and islands, and between wind farms with an inter-array cables inside the same wind farm park, or export cables linking the wind farm and the shore. So in this talk, we're going to present the application of the marine geophysical techniques that are commonly used to investigate the seabed and the subsoil for offshore wind farms and submarine cables projects. We present examples of results and potential constraints for the cable installations and the maintenance based on the acquired experience in offshore projects. So the workflow that we follow usually in this kind of projects is mostly the same. So we always start with a geophysical survey that provides the high resolution data of the seabed and the subseabed. Then, to guarantee the security during the geotechnical campaign and during the cable installation works, an UXO study is undertaken to identify any possible unexploited ordnance objects or artifacts. Thereafter, the geotechnical campaign is undertaken, and then the lab works. So when we combine the geophysical together with the geotechnical data, allow an accurate definition of the seabed characterization and the subsoil properties for a realistic design of the cable route, and if it is suitable to install a cable in that place. So the potential cable constraints, and in case to be necessary, a cable rerouting proposal, are provided as a source of information for the further cable installation and maintenance company. So we are going to focus in this talk with the physical methods and data and the potential cable constraints found in one project that were developed by Geociencias y Exploraciones Marítimas company. So before I start the geophysical campaign, the first of all is to find a corridor following the cable route, the predefining of the cable route. So in this corridor is where the superficial seabed and subsoil characterization and properties is determined, and with the high reliability for the design of the cable route. Then, for assessing the seabed characteristics, usually the survey areas are divided between onshore, which is the land or the immersed area, nearshore, which comes from 0 to 15 meters depth, and the offshore, which is deeper than 15 meters. At each survey area, different techniques, equipment, and work plans are defined, and also different vessels because of depth conditions. So in this presentation, we are going to focus on the nearshore and offshore geophysical techniques and results. The hydrographical and geophysical techniques that we are going to show here are basically comes from multi-beam echo sonder, which is used to obtain a high-resolution bathymetric map of the seabed and allows to characterize the seafloor topography and the relief. The side scan sonar data that is used to define the seabed morphology, the different sediments, and the sedimentary features of or natural or man-made objects on the seafloor. The sub-bottom profiler data is used to define, to identify the geological structures and the seismic stratigraphy of the subsurface, the sediment thickness, and the depth where is detected the rock, which is very important to cable burial engineering. And finally, the magnetometry data is used to identify any magnetic anomaly in the subsoil, being natural or anthropogenic. It can recognize objects up to several meters buried on the seafloor, depending on the survey requirements. And the magnetometry data also is key to ensure a safely cable installation. So, of course, other techniques can be also applied in these kind of projects, but always depends basically on the technical specifications of the projects, the topic, and the project site environment, settings, and conditions. Then, as we start with showing some results that we found, the cable route suitability is examined by using the integration and combination of all techniques and interpretation, as I mentioned before. However, special attention must be taken to those issues that could impose limitations on the cable installations and maintenance. These issues are defined as a potential cable constraints, and it could be such as seabed gradients, boulders, mobile sediments, hard sediments, other cables or paper lines crossing, fishing activity, etc. In this section, the results, we are going to show examples of potential constraints that we found in one project that were developed by a geotest company. But the project site cannot be specified because it has not developed yet and is one of the client's requirements. So sorry about that. For example, here we have two images of side scan sonar data of seagrass meadows that were detected with the side scan sonar, and depends on the area that they were in placed, the cable crossing can be forbidden. Other constraints can be the high seabed slopes that can cause hazards for the cable during installation or post-installation activities. Typically, the seabed gradients are classified in function of their slopes as very gentle, moderate, steep, and very steep. Our installation equipment are not suitable for stable and safe operations on steep and very steep seabed slopes. So is where these are which we are found. Here we have an example of a beach rock that were detected with the multi-beam echo sonder and the sub-bottom profiler that crosses a double cable route. So the beach rock was composed by two parallel ridges with 6 meters of maximum height and 80 meters apart. In this case, the multi-beam echo sonder provides information about the seabed topography, but also provides information of the seabed gradients that in the area were up to 15 degrees that were classified as steep and, as I said before, could be dangerous for the cable installation. The bottom profiler also gives information of the internal structure of this beach rock, detecting the reflectors of the two ridges and identifying that they are made of hard sediments or that they are separated by soft sands between them, as an example. The same example of the beach rock can be used for stiff and hard sediments and could be a potential hazard for a cable installation. So using the sub-bottom profilers, the hard sediment can be detected, and therefore the depth where they are can be defined in a continuity in the plan view. So the reflectors can be interpolated and create an isopack map. And this isopack map can be very useful for the cable burial depth and can be evaluated and validated. Other constraints is the presence of obstructions that could be a delay of the cable installations, for example, boulders or any feature identified over the seafloor. That should have different implications in the cable installations according mostly to their dimensions. So, for examples, a boulder can damage the burial equipment or reduce the burial equipment's capability to reach the required burial depth. So the boulders and the objects on the seafloor are usually classified, distinguished between their size as a small, medium, and big. And in the case of boulders, we usually found boulders as isolated boulders, like in the right up image, and as a boulder field in the left up image. Other objects can be ropes or wrecks or another anthropogenic debris, and that they are also constraints when installing the cable route, as it can be suspended from the seabed and represent a rope treat for the cable. Here is represented, for example, 2 wrecks that were found close to the cable route. But in this case, in this particular case, they were far enough to not be considered as a hazard. But the image are beautiful, and I like to share this kind of image. Other objects that sometimes are detected, but we are not able to identify, we usually classify them as USO, that means unidentified submerged objects. The topic of the mobile sediments can cause 2 types of constraints when installing the cable. So in the one hand, the cable can be buried more than expected, causing, for example, the overheating of the cable. Or on the other hand, the cable can be left exposed, leaving the cable vulnerable to be damaged. So bed forms such as dunes or sand waves or ripples are typically indicators of the sediment mobility. And here in these images, we show different ripples, morphologies, and dimensions that we found crossing the cable route. And for example, in the down image, we can see a ripple field that is superimposed to a mega ripple. So they are indicating that maybe 2 kinds of currents or directions are governing in this area. And of course, when we found mega ripples and dunes that they are of larger dimensions, they can produce larger amount of sediment movement. So using, for example, sets of multi-beam echosonder taken at different times, the bedforms mobility can be studied and defined as bedforms migrations, for example. And the cable crossing is another potential constraint for a cable installation and maintenance. Here, 2 examples I'm going to show of cable crossing. There's one is on the left, that there are 2 cables that are almost parallel to the cable route, to the proposal cable route. And the second one, which are the 2 images on the right, are an almost perpendicular cable crossing. So to simplify cable and people line crossing design, the best option would be to cross them as perpendicular as possible. This minimizes risk in future cable repair and maintenance operations. And finally, the fishing is an activity to consider also, particularly the demersal fishing. This activity could result in a snagging or damage of buried protected cable, and the minimum burial depth to protect cables from fishing tackles should consider cases when the fishing vessel performs multiple passes, resulting in a greater penetration. So here we have an image with trawl marks, and there is an issue that is very common in the seafloor that we use to see. So to sum up to the ideas that I would like you go at home, is that the ground model obtained integrating the geophysical and geotechnical techniques is the base of the investigation of the submarine seabed and assess properly the cable routes. And particularly the multi-beam echosonder, the side scan sonar, the sub-bottom profiler, and the magnetometry techniques are key to identify potential cable installations and maintenance constraints and guarantee the security during the works. The potential cable constraints leave the cable vulnerable to be damaged or make more difficult and sometimes impossible the cable installation works. And examples of these constraints shown are steep gradients because of beach rock outcrops, for example, boulders on the cable route, debris or man-made objects like wrecks, stiff sediments, fishing activities, and bed forms that can leave the cable exposed or overburied. So thanks for your attention. And if you have any question.